Hello and welcome to tutorial 20. Today we will be talking about disaccharides and polysaccharides. Before we get started, a quick reminder that the notes to accompany this video tutorial are available online through my website, and I do highly recommend that you print those out and have those in front of you because there are lots of structures already drawn for you in those notes. And so it's really to your advantage to have that in front of you so that you're not trying to frantically copy down the structures that I'm writing on the board. You'll already have that in front of you. All right, so with that said, let's go ahead and get started. So we learned in tutorial 19 that a carbonyl from either an aldehyde or a ketone can react with an alcohol to form a hemiacetal. So just a quick reminder of what a hemiacetal looks like. Remember that a hemiacetal has a carbon that's connected to an OR and an OH. Now, of course, carbon has 4 bonds. The other 2 bonds can be to either hydrogen or some carbon chain. So I'm going to write H/R. And that is going to just be dependent upon what aldehyde or ketone the hemiacetal came from. All right, so let me write here, hemiacetal. And just a reminder, carbon in a hemiacetal, a carbon is bound to an OR and an OH. Okay, that's what makes that a hemiacetal. Well, a hemiacetal can further undergo reaction with an alcohol to form an acetal. So we're going to write plus, we're going to draw some generic alcohol here, so HO, and then I'll just write R here. Remember that that stands for the rest of the molecule. So if this is methanol, then it's just a CH3. If it's ethanol, then it's a CH2, CH3. So we don't really care what the R group is, just some number of carbons. So let me label this alcohol. And we are not going to show a mechanism here. However, if you're interested in a mechanism, you can look that up easily online or in an introductory organic chemistry book. What I am going to do is draw an arrow that I hope will help you understand what new bond is forming in this reaction. But again, it's not a mechanism. The mechanism is much more complicated. All right, so I'm going to go ahead and indicate my lone pair of electrons on this oxygen of the alcohol. And I'm going to show the new bond that's forming here with the blue arrow when those 2 electrons form that new acetal linkage. And you're going to lose the OH from the hemiacetal. We had to lose a bond, right, if we're forming a bond. And the H from the alcohol. Those are going to come together as H2O, water. So water is a byproduct of this reaction. Okay. Now this reaction requires a catalyst. If you're doing this reaction in the lab, that catalyst is going to be an acid catalyst. So I'm going to go ahead and write H+ above the arrow here. And the acetal that forms is going to have a carbon connected to 2 OR groups. One was already present in the hemiacetal, okay? And then we've got the new one from the alcohol, okay? And then these 2 bonds didn't change. So still a bond to either hydrogen or some carbon chain, hydrogen and some carbon chain. So this is our acetal. And I'm just going to write a little note here. Notice that the carbon of the acetal is bound to 2 OR groups. Now those ORs need not be the same. Again, R just stands for the rest of the molecule. So this could be a CH3 and this one could be a CH2, CH2, CH3. They need not be the same. Don't forget your byproduct of this reaction, you also get H2O. Don't forget that. Okay. Now this reaction is reversible. Water can split apart that acetal, reverting it back to the hemiacetal and the alcohol. And any reaction where water is splitting apart a bond is referred to as a hydrolysis. So I'm going to label that reverse arrow hydrolysis. And we're going to see a lot of hydrolysis reactions when we get to digestion. Digestion is really just a whole lot of hydrolysis, splitting apart bonds with water. So maybe keep that reaction in mind for a future tutorial on digestion. All right. Well, disaccharides and polysaccharides form when monosaccharides link together via the formation of an acetal. So we're going to go ahead and erase here, and we're going to take a look at this reaction between two monosaccharides. Okay, so for our example of the acetal formation between two monosaccharides, let's just use two molecules of D-glucose. Okay, so if we draw D-glucose really quickly up here, remember that at the hemiacetal, the OH can either point up in the beta orientation when you draw the Haworth projections, remember these are called Haworth projections, or down, which is the alpha orientation in the Haworth projection. Now I'm going to be generic, and I'm just going to indicate that bond sticking straight out. And the reason I'm going to do that is because in an aqueous solution, we know from tutorial 19 that these monosaccharides are actually undergoing that mutal rotation. So they're converting from the alpha to the beta form via the acyclic monosaccharide form. So I'll just be generic here and go out. I won't indicate specifically alpha or beta, but all the other OHs have very specific orientation, which is what makes this D-glucose and not some other monosaccharide like D-galactose. Okay, and we're going to draw two of those. And again, I'm not going to specify alpha or beta. I'm going to leave that ambiguous. So another D-glucose. Okay. And let's go to our blue pen. Hopefully that'll make things stand out a little bit better here. Okay. So we've got our hemiacetal carbon here. So we know that this guy's going to be reacting. And I'm going to go ahead and number the carbons in this ring. Hopefully you remember from tutorial 19, the hemiacetal carbon is carbon number 1. And that goes back to the acyclic form where the aldehyde of the D-glucose is carbon number 1. Okay, and then when it reacts, it becomes this hemiacetal carbon. This is carbon number 2. This is carbon 3, 4, 5, and this one outside of the ring here is 6. Okay, do the same thing over here. 1, 2, 3, 4, 5, and carbon number 6. Okay. So the hemiacetal carbon can really react with any of these alcohol functional groups. We're just going to show it reacting with the alcohol off of carbon 4 because that's really the most common reaction we're going to be seeing when we're looking at our more common disaccharides and polysaccharides. Okay, so we're going to show the reaction with this alcohol here. So I'm going to go ahead and draw my lone pairs. I'm going to draw that arrow. Remember, that's not a mechanism. It's just meant to help you remember what new bond forms in this reaction. And then we're going to lose OH and H as H2O. Okay. All right, so what does our acetal look like? Our new product here. Okay, drawing all my OHs down, up. This one's going down, CH2, OH, but now that's part of our acetal. Okay, and then down, up. None of this stuff changes. Up with the CH2OH. And don't forget, plus H2O. All right, so where is our acetal? So here is the hemiacetal carbon, what was the hemiacetal carbon that reacted, and now notice that it's connected to an OR group here and an OR here. And so this is our new, I'll highlight it here, this is our new acetal linkage. Now the acetal linkage in a sugar is more commonly referred to as a glycosidic bond. So I'm going to label that both ways here. Okay, so this is our acetal linkage, which in sugars is referred to as a glycosidic bond. So from now on, you will hear me refer to that linkage as a glycosidic bond. Okay. Now let's go back and put these numbers in. Okay. So we had carbon 1, 2, 3, 4, 5, and 6. And I'll go ahead and circle those just to be consistent. Okay. Same thing over here. 1, 2, 3, 4, carbon 5, and carbon 6. Okay. So we showed a reaction between the hemiacetal carbon, which is carbon 1, and the alcohol off of carbon 4 of the other monosaccharide. And so that makes this glycosidic bond more specifically, and in fact I'm going to write it in a different color because I really want it to stand out. More specifically, this is called a 1, 4 glycosidic bond. Now notice that it points down, which is the opposite orientation of the CH2OH. When we learned about monosaccharides back in tutorial 19, remember that if the OH of the hemiacetal was in the opposite direction of the CH2OH, remember that that was the alpha orientation. Same thing goes with the acetal. So this is an alpha 1,4 glycosidic bond. Alpha because the glycosidic bond is pointing down, which is opposite direction with respect to the CH2OH, which is always going to be pointing up there in the D-glucose unit. And it's 1,4 because we're connecting carbon 1 from the first glucose molecule to carbon 4 of the second glucose molecule here. And then of course it's a glycosidic bond. Glycosidic bond is the term that we use for the acetal linkage in a sugar. So an alpha 1,4 glycosidic bond. Now hopefully you've already realized that that means that this bond can form also in the beta orientation. So let's show, and let's do arrow this way. Let's show that reaction as well. That's going to make a completely different disaccharide with different chemical and physical properties. Okay, so let's show those two D-glucose units connected with a beta 1,4 glycosidic bond. So that would mean that the glycosidic bond formed with this up orientation. It's going to be on the same side as a CH2OH. Sorry, it takes me a little time to draw these. Okay, and don't forget plus H2O. Okay, and I'm going to go ahead and highlight our acetal linkage, the glycosidic bond there. Okay, and remember that it is an acetal because now this carbon is connected to an OR and an OR, so two OR groups, okay? And in this orientation, when it is on the same side, they're both pointing up, as the CH2OH, it is the beta orientation. So this is a beta 1,4 glycosidic bond. Okay, so again, beta because of the orientation of the glycosidic bond. It's pointing in the same direction as the CH2OH. That's the beta orientation. 1,4 because we're connecting the first carbon of that first monosaccharide to the fourth carbon of the second monosaccharide. And then of course it's a glycosidic bond. All right, so I mentioned before that orientation of that glycosidic bond, whether it's alpha or beta, that results in two completely different disaccharides. The first is a very common disaccharide called maltose. Okay. Two D-glucose units connected by an alpha 1,4 glycosidic bond make the disaccharide known as maltose. Two D-glucose units connected by a beta 1,4 glycosidic bond makes a completely different disaccharide known as cellulose. And the maltose is completely digestible by animals. So we can digest maltose and obtain glucose, which can be metabolized for the production of energy, keep our cells alive. But cellulose, made up of D-glucose, cannot be metabolized by humans. That beta 1,4 glycosidic bond cannot be broken by any of the enzymes in our body. And so even though it's made up of D-glucose, we can't obtain energy from it. There are some grazing animals who can. So cows and sheep who eat grass, which is mostly made up of cellulose, can break down that beta 1,4 glycosidic bond in both cellulose and the cellulose. Termites, which gnaw on wood is mostly cellulose as well, they can break down, again, that beta 1,4 glycosidic bond present in both cellulose and cellulose, but humans cannot. Okay, so two very different disaccharides, all because of that little difference in the orientation of the glycosidic bond. Okay, so if you're thinking, oh, this is kind of trivial, who cares if it points up or down, it's not trivial. It's actually very, very important how these monosaccharides link together. All right, so let's go ahead and erase here and start talking about some of the more common disaccharides and polysaccharides. Okay, disaccharides form when just two, of course meaning two, monosaccharides link together by a glycosidic bond. So I'm going to write that up here. Form when two monosaccharides link together via a glycosidic bond. And we're just going to look at the three more common disaccharides. So starting with maltose. So we're just going to look at the more common disaccharides. Starting with maltose. And I know we already saw the formation of maltose in our previous example, but we'll go ahead and go through it again because, you know, this is kind of complicated and seeing it again can be very, very beneficial. All right, so first of all, where might we find maltose in nature? Well, maltose is formed from malted barley in the production of beer. Maltose is also an intermediate during the digestion of starch. So when animals are digesting starch, maltose is one of the intermediates formed. It then gets broken down into glucose ultimately, which is what we obtain the energy from. And maltose is also one of the less common sweeteners that you might see added to packaged foods. Again, less common. More common, you're going to see sucrose and glucose and things like that. All right, so maltose forms when two D-glucose units react and form an alpha 1,4 glycosidic bond. We just saw that a moment ago, but let's go ahead and write that down here and then show it just one more time. So maltose forms when the acetal, or excuse me, the hemiacetal, when the hemiacetal of one D-glucose unit reacts with the OH off of carbon number 4 of another D-glucose unit. Creating an alpha 1,4 glycosidic bond. Okay, and real quick, go through that reaction again. So we've got two molecules of D-glucose. And again, I'm not going to specify alpha or beta here because we know that in solution we would have both, as well as the acyclic form. Down, up, down, up. The orientation of all these other OHs is important. Remember, that's what makes it D-glucose and not some other monosaccharide. Okay, and draw that again. Down, up, down, up. That one's a little sloppy. Sorry about that. All right, and again, we're not showing a mechanism here, but I do still think it is helpful to show where that new bond forms. So I'm going to do that. Before I do that, let me just label these carbons 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. Okay, new bond forms. You lose the OH and the H as H2O. Okay. Oops, let me label that D-glucose. All right, and the disaccharide that forms, we already know is going to be maltose, so we're going to have an alpha, so orient that down, an alpha 1,4 glycosidic bond, down, up, down, up. Okay, and then we're going to go down, up, down, up. Don't forget your byproduct is H2O. And now this is a disaccharide known as maltose. And just a quick reminder of what makes it an alpha 1,4 glycosidic bond. Okay, so we're talking about the acetal linkage, the glycosidic bond. Remember in sugars, we're going to call it a glycosidic bond. Okay, and with respect to the orientation of the CH2OH, it is in the opposite direction. It is down instead of up, so that's what makes it alpha. And remember that we're connecting carbon 1 from this first D-glucose unit to carbon 4, because it reacted with the alcohol off of carbon 4 to carbon 4 of the other D-glucose unit, and that's what makes it an alpha 1,4 glycosidic bond. Okay, so a couple more things about maltose before we go on and talk about our other two more common disaccharides. Notice that the hemiacetal in the first glucose unit reacted and now is tied up in the acetal. The acetal cannot undergo mutarotation. Okay, so you would not expect this to be switching between the alpha and the beta form. It's no longer a hemiacetal, a free hemiacetal. It is an acetal. However, the hemiacetal of the second glucose unit is still a free hemiacetal. Okay, so let me label that here. We still have a free hemiacetal on the second glucose unit of the disaccharide maltose. That free hemiacetal can undergo mutarotation. And that's why I've drawn the kind of generic orientation. I haven't specified either alpha or beta because this can undergo mutarotation and interconvert in an aqueous solution between the alpha and the beta form. And remember, it does that, we learned that in tutorial number 19, by going through the acyclic form. Okay, and remember that the acyclic form has the aldehyde and the alcohol rather than that hemiacetal. All right, so what does this mean? This means that maltose is what we call a reducing sugar. It actually does contain a free hemiacetal which can undergo the mutarotation and therefore form the acyclic form of the D-glucose unit, okay, which has a free aldehyde and an alcohol. Instead of those being tied up in the hemiacetal, it has a free aldehyde. Well, an aldehyde can undergo oxidation. So maltose can be oxidized via that free aldehyde. Now, if it gets oxidized, that means that something else has to be reduced. And that's why maltose is called a reducing sugar. It can cause another substance to be reduced by being oxidized itself. So let's write that down here. Note, maltose has a free hemiacetal. In the acyclic form, the aldehyde can be oxidized. This makes maltose a reducing sugar. I'm going to underline reducing sugar. it can be oxidized and therefore causes something else to be reduced. And that's a really common thing to test for in an introductory biochemistry lab. So you very likely will be doing a lab where you're testing different sugars to see if they are reducing sugars. Okay, that's what they're talking about. Does it have a free hemiacetal, which can undergo metarotation, therefore meaning it has a free aldehyde, which can be oxidized, causing something else to be reduced. All right, let's go on to our second common disaccharide, which is going to be lactose. Okay, the next common disaccharide that we're going to talk about today is lactose, sometimes called milk sugar because it is the major carbohydrate present in mammalian milk. And lactose forms when D-galactose is connected to a D-glucose unit via a beta 1,4 glycosidic bond. So let's write those details up here. Lactose forms when the hemiacetal of a D-galactose unit reacts with the OH off of carbon number 4 of a D-glucose unit, creating a beta 1,4 glycosidic bond. Okay, so let's write that reaction out. So starting with D-galactose, which has down, up, up, and then a CH2OH. Remember that the orientations of these alcohols is relevant to the identity of the monosaccharide. So that orientation is for D-galactose. Okay. And it's going to be reacting with D-glucose, which is down, up, down, and then the CH2OH is up. Okay. So again, not a mechanism, but just a method that will hopefully help you to remember what bond is forming here. Okay, we're going to get a bond forming, and let me number these carbons really quick. So that's going to be connecting carbon 1 to carbon 4 here. And then we're going to lose the OH and the H as H2O. Okay. So what does our new disaccharide look like? We're going to draw our galactose first. And remember, it's going to be a beta 1,4 glycosidic bond, so my glycosidic bond is going to be pointing up, same side as the CH2OH, and then all of these OHs stay the same, so down, up, up. Okay. Here's our new glycosidic bond. And this is the glucose unit, so down, up, and of course that one's down. We've got CH2OH plus H2O. Okay. So let's go to the green and let's Make sure that everyone can see our new beta 1,4 glycosidic bond present in the disaccharide lactose. I'm going to highlight it here. This is our beta 1,4 glycosidic bond. And again, it's beta because the orientation is up. It's on the same side as the CH2OH, which is also in the up position in these Hayworth projections that we're drawing here. And let's also number our carbons so that we can see that it is a beta 1,4 glycosidic bond. All right, so once again, hopefully you can see that the disaccharide lactose has a free hemiacetal. It's the hemiacetal of the glucose unit. The hemiacetal of the galactose component is now tied up as an acetal. Okay, so it is no longer a free hemiacetal, but the glucose component does have, and I'm going to go ahead and label it here. Whoops, let's go back to the green. Does have a free hemiacetal, which means that lactose is also a reducing sugar. Because that free hemiacetal is free to undergo mutant rotation in an aqueous solution, that means that when it is in the acyclic form, it does have a free aldehyde. Aldehydes can be oxidized, therefore causing something else to be reduced. So lactose is a reducing sugar. So let me write that down here. Note, lactose has a free hemiacetal, thus it is a reducing sugar. Okay. So let's go ahead and erase here and talk about our third and final common disaccharide, which is going to be sucrose. Okay, the last disaccharide that we're going to talk about is sucrose, common table sugar, the most common sweetener used in packaged foods. And sucrose is formed when D-glucose reacts with D-fructose to create an alpha-1 beta-2 glycosidic bond. So let's write those details up here. Sucrose forms when the hemiacetal of a D-glucose unit reacts with the OH of the hemiacetal, which is more specifically a hemiketal in fructose. So I'm going to write in parentheses here, hemiketal, because it came from a ketone, of a D-fructose unit, creating an alpha-1 with respect to the glucose, beta-2 with respect to the fructose glycosidic bond. Okay, so let's take a look at that reaction. So let's draw our D-glucose. our D-fructose. And fructose is a little different because, again, fructose is actually more specifically a hemiacetal, meaning that instead of having a hydrogen off of the hemiacetal carbon like glucose does, it has a CH2OH, so it has an R group. And so I'm going to go ahead and put the OH in the beta position just because I have to specify where the CH2OH is as well. So I'm going to go ahead and make a beta D-fructose here. Up, down, and CH2OH. And we better number our carbons here because this one is a little bit more tricky than the last two we looked at. So let's take a minute to do that. So we've got carbon 1 is the hemiacetal carbon here. Carbon 2, 3, 4, 5, and 6 for D-glucose. And then we actually start here with our numbering, and if you don't remember why, you might want to look back to tutorial 19. Again, fructose is a hemiacetal because it came from a ketone, and the ketone is at the 2 position. And so this carbon was the carbonyl of the ketone, and that's why this is number 2 and this is number 1. 3, 4, 5, and 6. Okay, and again, this is D-fructose. Okay. And so, we're going to get a reaction between the hemiacetal carbon, carbon 1 of the D-glucose, and the OH off of the hemiacetal of fructose. So this is the alcohol that's going to react, the OH off of the hemiacetal of the D-fructose. So take a minute and make sure you can see that. Okay, why I'm picking this one. That's what we said right here. Okay, the OH off of the hemiacetal, which is more specifically a hemiacetal of the D-fructose. So draw your arrow. Again, not a mechanism, but hopefully helps you remember the new bond that's forming. And the old bonds that are breaking, OH and H come together, do it this way, to make H2O. Okay. So what does our new disaccharide, sucrose, look like? So we're going to have our glucose here. It's going to have an alpha, so this bond is going to be going down. I'm going to write OH, down, up, down, and then our CH2OH. So alpha pointing down with respect to the glucose and forming that glycosidic bond to the D-fructose. Okay, so here's our oxygen and here's our new bond. Okay, and we've still got the CH2OH here. Everything else remains the same, so up, down, CH2OH. Don't forget plus H2O. Okay, and just to make it as clear as I can make it, because I know this is complicated stuff, I'm going to number the carbons in my rings so that you can really see that it's carbon 1 from glucose reacting with the OH off of carbon 2 of the fructose. Okay, so we've got carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6 for our glucose. We've got carbon 1, 2, 3, 4, 5, and 6 in our fructose. So we can see that we have the alpha orientation, okay, for the glycosidic bond with respect to the glucose. So alpha 1, but it's connected to the hemiketal of the fructose as well. So we have a second glycosidic bond which is oriented up on the same side as the CH2OH. So beta 2 with respect to the position at the second carbon of the fructose, glycosidic bond. And I should actually do this. So I'm referring to that whole unit there. Okay, so alpha 1, beta 2, glycosidic bond. All right, so last thing I want to say about sucrose is that notice that it does not have a free hemiacetal. Okay, the hemiacetal of glucose reacted with the hemiketal of the fructose, and so therefore they're both tied up in that new glycosidic bond. So no free hemiacetal, which means that sucrose is not a reducing sugar. It cannot be oxidized, or will not easily be oxidized, thus reducing something else. So let's write that here. Note, there is no free hemiacetal in sucrose. Thus, sucrose is not a reducing sugar. All right, so let's go ahead and erase here and go on to polysaccharides next. Okay, turning to polysaccharides, which begin on slide 5 of the notes. So poly means many, so not surprisingly, polysaccharides form when many monosaccharides link together via glycosidic bonds. Now we're going to talk about some of the more common polysaccharides, starting with cellulose, and you'll notice that I already drew the pictures that appear in the notes on the board because I didn't want you to be sitting there waiting for me to draw these fairly complex structures up here. All right, so I went ahead and did that in advance. Cellulose is a major structural component of plants. It is composed entirely of D-glucose, and those D-glucose units are linked together by beta 1,4 glycosidic bonds. So you'll see that I've drawn 2 D-glucose units linked together right here. Let's do that in green by a beta. Beta because of the orientation, which is up, which is the same orientation as the CH2OH. So beta 1,4 because it connects the first carbon here of this glucose ring to the 4th carbon of the neighboring glucose ring. So beta 1,4 glycosidic bonds. Okay, and notice I put this in parentheses because I'm just showing 2, but this is not a disaccharide, it's a polysaccharide, so there would be many more units repeating on both ends. All right, now we are sort of limited in understanding the structure of cellulose if we just look at the glucose rings in the Haworth projection. Remember that this method of drawing these rings is called the Haworth projection. In truth, those six-membered rings are not flat hexagons. Remember that they are puckered so as to accommodate that tetrahedral geometry, which is 109.5 degree bond angles here. Okay, so I've redrawn cellulose in a very complicated looking structure. I've redrawn it so that you can get a better feeling for what this structure really looks like. Okay, so let me help you understand these individual glucose monomers in what's called this chair configuration that we've drawn them here, which is more like how they actually exist. All right, so we've got a glucose ring here. Let's number it. Okay, so here's the oxygen from the ring, and this is carbon 1, 2, 3, 4, 5, and then here's carbon 6, the one that goes out of the ring, the CH2OH. Okay, so let's do the same thing over here for this individual glucose monomer. So here we've got the oxygen in the ring, and then carbon 1, 2, 3, 4, 5, and 6. So notice that this ring is oriented upside down with respect to how we've had it drawn here in the Haworth projection, and then this one is more right side up. Okay, so the oxygen in the ring followed by carbon 1, 2, 3, 4, 5, and 6. Okay, so that's more like how we're used to seeing it here in the Haworth projection. Now, what I want to show you is how to interpret the beta-1,4 glycosidic bond in this chair configuration, in this orientation that it's drawn here. Okay, so we see, let's go to the green, our glycosidic bond right here, connecting the 1 and the 4 positions of these neighboring glucose units. Okay, now you might be thinking, well, it's pointing down, isn't that alpha? Note that it's still oriented in the same direction as the CH2OH, and that's what makes it either alpha or beta. So pointing up, and the CH2OH is also pointing up, so they're on the same side, that's what makes it beta. Well, our CH2OH in this chair configuration for this first glucose ring, it's pointing down as well. Okay, so they are on the same side. So let's see, let me try to indicate that here. On the same side. Okay, so it is showing a beta orientation, and of course it's 1,4 because we already said it's connecting the 1 and the 4 position, and it's a glycosidic bond. Okay, now why is it important to look at the structure of cellulose in this configuration? Because this is really the configuration that the glucose molecules take on, this chair configuration. And it allows this extensive network of hydrogen bonding to occur, not only between neighboring glucose units in the polysaccharide chain, but also in glucose units that are much farther away on the polysaccharide chain as well. And I've indicated all of my hydrogen bonding opportunities with these reddish pink dots, the dot, dot, dot. So the 3 red dots are indicating hydrogen bonding that's occurring, again, between neighboring glucose units as well as glucose units that lie much, much further down the chain. And this results in a very strong, fibrous structure that we know as cellulose or cotton. All right, so hopefully that helps you understand that drawing that I have on slide 5 just a little bit better. And my point here is to really show you that extensive hydrogen bonding, which leads to that very strong, fibrous structure of cellulose. Okay, let's go on to our next polysaccharide, which is going to be the polysaccharides present in starch. Plants store glucose as starch, and starch is actually a mixture of two main polysaccharides. And we're going to talk about the structure of each. So let's write A here for the first, which is amylose. And amylose is a polysaccharide composed of D-glucose units which are connected by alpha-1,4 glycosidic bonds. So I'm going to write here, composed of D-glucose units connected by alpha-1,4 glycosidic bonds. Okay, well, we already know what that looks like, so I'm just going to draw that really quickly here. And it's glucose, so down, up, down, and then up, down, up, that one's down, and CH2OH is up. And of course it's a polysaccharide, so I'm going to go ahead and put parentheses here indicating that of course this chain goes on and on and on for hundreds or even thousands of D-glucose units. Now, unlike cellulose, where that long chain wraps around and folds and creates all this opportunity for hydrogen bonding, which causes cellulose to have a very rigid, strong structure. The amylose does not fold upon itself like that. It actually will take on a coiled structure. So that long chain of glucose will have a coiled structure. All right, the other main component of starch is amylopectin. So let's write down here, amylopectin. And amylopectin is also composed of D-glucose units that are connected by alpha-1,4 glycosidic bonds, but it differs from amylose in that it also has branched chains of D-glucose coming off of that primary chain, which are linked to that primary chain by alpha-1,6 glycosidic bonds. So let's take a look at that. Okay, so let's write up here first, composed of D-glucose units connected by alpha-1,4 glycosidic bonds with branched chains of D-glucose that are connected by alpha-1,6 glycosidic bonds. Okay. All right, so let's draw that down here. So again, we're just going to have that regular old alpha-1,4 glycosidic bond, just like we had up there for amylose. And I'll put parentheses here because it's not a disaccharide. Remember, we're talking about, thousands of glucose units. We're talking about very large polysaccharide structure here. Okay, and then on this D-glucose unit, okay, I'm going to also show the branch here that creates the alpha-1,6 glycosidic bond. Okay, so we're going to have a CH2O running out of room. Sorry, this is a little bit messy. Hopefully you have the notes, which has this drawn very nice and neatly. Okay, and again, that chain's going to be repeating on and on, those glucose units. And I've got to squeak in here, so sorry again if that's getting a little bit messy, that CH2OH. Okay, so let me label both my alpha 1,4 glycosidic bond. Okay. Alpha because it is in the opposite direction as the CH2OH. Okay. And 1,4 because it's connecting the 1 position of one glucose to the 4 position of another glucose. And then let me label over here my alpha 1,6. Okay. So this is my alpha 1,6 glycosidic bond. And it's alpha 1,6, again alpha, because with respect to the CH2OH, it's on the opposite side. And 1,6 because it's connecting the 1 position of this glucose branch to the 2, 3, 4, 5, 6 position of this other glucose unit. Okay. Again, drawn a lot nicer in your notes. Okay, so let's go ahead and erase here, and we'll go on to talk about our final polysaccharide, which is going to be on slide 6, glycogen. Animals store glucose in the form of glycogen, which is found mainly in the liver and the muscles. And glycogen is a polysaccharide composed of D-glucose units connected by alpha 1,4 glycosidic bonds with branching chains of D-glucose, which are connected to that primary chain by alpha 1,6 glycosidic bonds. So if that sounds a lot like the structure of amylopectin, you're right. That's very much the description we use for amylopectin. So how do these two polysaccharides differ then? Well, the amylopectin has branched groups approximately every 25 glucose units in a chain. The glycogen is much more highly branched. It's going to have those branch chains coming off of approximately every 8 to 12 glucose units in the chain. So very similar structures, but glycogen is more highly branched than amylopectin. So let's write that description up here. Glycogen forms when D-glucose units are linked by alpha 1,4 glycosidic bonds with branched chains of D-glucose connected by alpha 1,6 glycosidic bonds. Okay, so again, let's go ahead and draw that because my last attempt to draw that I was running out of room and it was getting a little bit sloppy. And again, this is in your notes. This is on slide 6. Okay, so much better drawing in your notes. All right, so we've got our alpha 1,4 glycosidic bond here. And this is a polysaccharide, so I'm just going to indicate parentheses. This is going on and on and on. There are thousands of glucose units in these polysaccharide structures. And it's glucose, so down, up. That one's going down. And CH2OH. And down, up, down. And then I'll make this my alpha 1,6 linkage. I could have made it this one It doesn't really matter. It's going to be about every 8 to 12 glucose units in that long polymer chain. All right, so we've got a CH2, and it's the OH off of that 6th CH2 that's going to react and form our glycosidic bond. Okay. All right, that's a little bit better. All right, and then of course this chain, this branch coming off, it's going to have a bunch of D-glucose units as well, and they're going to be connected again by that alpha-1,4 glycosidic bond, and then maybe 8 to 12 units down that chain, there'll be an alpha-1,6 branch. So I'm just going to put a parenthesis here because this chain also goes on. And let me go ahead and label both my alpha-1,4 and my alpha-1,6 glycosidic bonds. Okay, so here, we're probably more familiar with seeing this one. We've seen this one quite a bit now. We've got our alpha, because it's on the opposite side with respect to the CH2OH. Okay, so we've got alpha orientation, and it's connecting carbon 1 of this glucose unit to carbon 4 of the other neighboring glucose unit. So it's an alpha-1,4 glycosidic bond. And then over here, we've got a glycosidic bond as well, okay? And it's connecting, it's alpha, because again, it's on the opposite side of the CH2OH, and it's connecting carbon 1 to carbon 6 of this other glucose unit. So let me go ahead and label these 2, 3, 4, 5, and this one's 6. Okay. So this is an alpha 1,6 glycosidic bond. Okay. And last thing I want to do, and then we will be all finished for the day, is just give you a nice visual to show you the difference between amylopectin and glycogen, because again, the descriptions are very similar. They're polysaccharides composed of D-glucose. Those D-glucose units are connected by alpha-1,4 glycosidic bonds, and then there are branched chains of D-glucose that are connected to that primary chain by an alpha-1,6 glycosidic bond. So they both have that same description. Remember in amylopectin that those alpha-1,6 branches occur approximately every 25 glucose units in the chain. Remember that in glycogen, they occur about twice as often. They occur about every 8 to 12. So really 2 to 3 times as often. About every 8 to 12 glucose units, you're going to have a branched alpha-1,6 glycosidic bond leading into another chain of glucose units which are connected by alpha-1,4 glycosidic bonds. So a nice drawing for that. Let's draw amylopectin first. Is to just show that chain of glucose as a line, okay? And then let's say that this represents about 25 glucose. We're going to show the alpha-1,6 branch coming off about every 25 glucose units. So I'm going to write approximately 25. Approximately 25 later, so that would be about 50 from the start. You're going to have another branch. And approximately 75 from the start, you're going to have another branch. And then off of those branches, you can also have branches. Okay, so about 25 units up this chain, and about 25 up this chain, and about 25 up this chain as well. Well, if you look at the similar type of drawing in glycogen, okay, so here's our chain of glucose units. We're going to have these branches occurring more frequently. Let's just say, since it's 8 to 12, let's just say about 10. Okay, let's just average it out there. So about 10 So then about 20 for this branch from the start, about 30, about 40, approximately 50, okay? And then off of these branches, you're gonna have branches as well. About every 10 glucose units up the chain. And then even off of these. So about 20 from the start here. So you can see a much more branched structure, much more highly branched structure in the glycogen than you do in the amylopectin. Again, about 2 to 3 times as many branches coming off of your primary chain. Okay, so that will conclude our tutorial number 20. It was a lot of work and a lot of structures to draw, but I hope it was helpful to you, and I really hope that you will consider tuning into problem set number 20 to help you solidify all this knowledge that you've learned in tutorial 20. Thank you very much.